Hello class, and welcome to my final presentation for data structures and algorithms. This will be a summary of everything that we've learned and everything that we've gone over. So without further ado, let's get started. So what is a data structure? A data structure is a way of organizing our data. It defines our relations between data and it enables more efficient use in the handling of our data. So how does that apply to software development? Well, more efficient code. It's very necessary for larger applications, and it enables better organization of our data. So when writing an application or a program, um, it just makes everything a lot cleaner and more efficient. So, and we'll get into time complexities. Um, but it makes for a much more efficient application, and especially if like you need to go in and maintain someone else's application or maintain your own application, knowing how that data is being handled and being organized is just nothing but beneficial to you and other software developers. So we have two different types of complexity. We have space and time complexity. Space complexity is the amount of space required by an algorithm, so that is how much memory allocation is needed for the data that you're handling or that you're storing. And time complexity is the amount of time required by an algorithm to execute. So that is how long does it take this algorithm to iterate through all the things that it needs to iterate to and get the data that we need. And there are two different types of data structures. We have linear and nonlinear. Linear data elements are arranged sequentially. Every element is directly attached to its neighbor. It is single level. And examples include arrays, linked lists, queues, and stacks. And I like to use a linked list as an example. As we can see, it's single level. Everything is sequential. Everything is attached to its neighbor. Arrays do the same thing. They're similar enough anyway. But I prefer linked lists. I like them a lot. Then we have nonlinear. They are data elements that connect in a hierarchical nature. Multi-level, comparatively harder to traverse, as we can see between these two images. And examples include trees, graphs, and maps. And the example provided here is a graph. We don't really need to get into how that works so much. Well, I can explain it. So a graph is comprised of nodes, or which is in the case of a graph, they're considered vertexes or vertices. Each vertex is connected to another through an edge or a line, and that's what connects them. They can get pretty crazy, as we can see here. And the structure that you use is really just dependent on your needs for your application. But yeah. So we're going to go over different types of data structures now. We're just going to briefly summarize what each one does. We're going to go over arrays, linked lists, stacks and queues, hash tables, and tree structures. So an array, I think we all started here when programming. When we started programming, it's the most basic of all data structures. It is linear storage of the same type of data, sequential collections, linear traversal, and it is indexed base. So every element in the array has an index value starting from 0. And that's kind of all there is to say about an array. Yeah. And then we have linked lists. We have a singly linked list and a doubly linked list. Each list is comprised of nodes. Each node is made up of a data value and a pointer. Obviously, you can have nodes with more than one data value. This is just the most simple example of it. A singly linked list only has next pointers, so it can only point forward. You can only traverse forward. A doubly linked list has a next and a previous pointer, so you can move forwards and backwards in it. Next, we have stacks and queues. Stacks are kind of self-explanatory. Every element that gets added, the next element gets added on top of it. And it follows the last in, first out principle. So the last element added is the first one popped off. I usually think of a stack of pancakes. Excuse me. Um, you don't start eating the pancakes with one on the bottom, you start at the top and you work your way down. That's kind of how stacks work. Queues are similar to stacks. They're usually depicted more horizontally. Um, the element at the front is popped or dequeued first, and anything appended is always the last to go. There are priority queues in which every node has a priority value, and when that's determines how it is inserted. Um, but regardless, however it's inserted, the one at the front's always going to be popped off first. Um, but I mean, whatever type of key you have, it's going to follow that first in, first out um, principle. Next, we have a hash table. This is my favorite data structure. I just think it's really cool. Data is organized in two buckets. Buckets are decided by an element's hash value, and a hash value is determined by the modulus value of the element being added. So, what that means, our buckets are kind of aligned in like an array. It is index based like an array. I don't know if it's referred to something different. I just think it's basically an array of buckets, just an array of null values that you add values to. The inputs, where those inputs are added or where those insertions are added, are dependent upon the modulus value or the hash value of that insertion. So the way that you determine that is you take the size of your array, so in this case it's 7, and you divide that by your insertion value, and the remainder of that division equation determines what bucket it goes in. So in this case we have 7. 7 divided by 7 is 0, so that goes in bucket 0. 16 divided by 7 has a remainder of 2, that goes in bucket 2, so on and so forth. Now, if you have an insertion with that ends up with the same hash value, you come into a collision. So let's say we get another 7. That remainder, that hash value is 0. Tries to go into 0. Uh-oh, there's already a value in there. There are several ways that you can handle this. My favorite way is just to turn that bucket into a linked list. So whenever you have a collision, you just add it to the back of it or you append it. There's another collision method where you just search for the next empty bucket and you just stick it there. I prefer the linked list method because I just think it's neater and it keeps it more organized. I feel like, and I'm sure it depends on the use case of your application or what your needs are, but that's my personal preference is just make it into linked list. Um, but yeah, that's a hash table. Next, we have trees. Trees come in many shapes and sizes. Um, every tree is basically composed of the same parts. We have every tree starts with a root value. That's just the first value added. And then every node most nodes will have a left and a right child. It has up to a left and a right child. A leaf is a childless node, so it's just the very end of the tree. An internal node is any node with a child. It can be 1 or 2, which is also referred to as a parent node. And then an ancestor node is um, any node above a specific node's parent. So if we're referring to H here, D is a parent, B is the grandparent or the ancestor. And then these would be considered uncles and aunts or aunts, depending on who you ask. But any root above H or whichever node that we're talking about besides the parent is going to be its ancestor. Every tree has a level value, which is determined by how deep the tree goes. So this has a level of 3. So we have 0, 1, 2, 3. Or it has a height of 4, I apologize. It's a height of 4. 0, 1, 2, 3, that gives it a depth of 4, which gives it a height of 4. We have a binary search tree, which is a specific type of tree. It's just got a special organizational property. Any new node added is going to be either inserted on the left or the right subtree. And that is determined by the value being inserted. So let's take 16 here. 16 is less than 20, so it's going to be on the left subtree. And if the value was greater than 20, go on the right. So left is always less than, right is always greater than. So we have 16. 16 is less than 20, so we have 10. We compare it to the 10. 16 is greater than 10, so we have 15. 16 is greater than 15, so we move it to the right of 15. There's nothing left here to compare it to, so there it stays. Same with the greater than value, 45. 45 is greater than 20, greater than 40. 45 is less than 50. So we put it down the left side of 50. There's nothing else here to compare it to, so that's its new home. And then anything inserted to a tree is referred to as a key. Next, we have the big boy, the red-black binary tree. This is similar to BST with more strict rules. It still kind of follows the same organizational property. So the left subtree is less than the root node. The right subtree is greater than the root node, but it has a few extra features to it. Each node is either red or black. The root node is always going to be black. Red nodes, you cannot have adjacent red nodes. You can't have adjacent black nodes. All null pointers are considered to be black. The tree is auto-balancing, so if you remove something or you add something and it needs to, and it no longer adheres to the integrity of the tree, the subtree that you're looking at will either rotate right or left in order to maintain the integrity of it. All paths from the root node must have the same number of black nodes. So if we look at this tree here, every path has a total of 3 black nodes down it. So we have 1, 2, 3, 1, 1, 2, 3, and so on and so forth. And every path has at least 3 black nodes of it. And like I said earlier, lesser than 13 is going to be on the left, greater than 13 is going to be on the right. So pros and cons of a binary tree versus an array. Binary trees are nonlinear. They tend to be more organized. They're better used if insertion or deletion is going to be involved. And I think that they're better used for storing larger amounts of data. Whereas our linear, they're simpler, they're easier to traverse, and they're better. I think they're better used for smaller or more static data sources. So if you're not going to be adding anything to it, you're just going to be storing data, I think arrays are the way to go. But it really just depends on your use cases and what your needs are, and that just depends on your needs. So next we'll be going over data structure traversal, which will be a really general overview of searching, insertions, and deletions. Searching is pretty much in all cases, it's going to be comparing the structure's elements to key values. So if you have an array and you're looking for 5, you could either do a linear search or a binary search looking for that data value. And that's pretty much going to be the same across all structures, is you're just going to be comparing a key value to what's within the structure. And if there's nothing there, you'll return null or 0 or however you write it. Insertion, I'm using linked lists as an example because I think they're the simplest to visualize. But it always varies depending on the data structure. In a linked list, it is performed by either prepending or appending a new node to a value. Prepending takes the head pointer and changes its pointer to the value of the new insert. Appending takes the last value and just takes that last this last value and changes its pointer to the new insert, and that new insert will then point to null, showing the tail end of the list. And then removal or deletion. Deletion also varies depending on the data structure, but in a linked list, a node is removed by reassigning the pointer values of the nodes adjacent to it. So in this visual here, we want to remove C. We assign that C to a temporary value, and then we overwrite the pointer of B and we assign it to D, and then that removes the node that we no longer need. So next we have commonly asked questions and answers. So let's get started. How is an array different from a linked list? Arrays are fixed in size. Linked lists are dynamic, which is why I prefer them. Insertion and deletion as a list is a lot easier in an array, but more memory is needed for a linked list due to the pointers for the nodes. When is a binary search best applied? It is best used for lists or arrays that are already in sorted order.